the cross product, also called the vector product. So, two vectors are orthogonal if they meet at right angles, and this means that their dot product is 0. Remember, B dotted with C is equal to the length of B times the length of C times cosine of theta, where theta is the angle between them. And if theta equals 90 degrees, then that means that cosine of theta is equal to 0, and so B dot C is equal to 0. Conversely, if theta is not equal to 90 degrees, or I guess 270 degrees, then as long as B and C are non-zero vectors, then their dot product is not going to be 0. Alright, anyway, given two vectors B and C, we would actually like a method for finding a vector that is orthogonal to both of them. So in other words, we want to get this normal vector n that meets both B and C at 90 degrees. And then as we talked about it before, it's also going to be equal to 90, it's also going to meet every other vector in the plane spanned by B and C. It's also going to meet every other one of those vectors at 90 degrees as well, because W is a linear combination of B and C. W is equal to lambda times B plus mu times C. Anyway, one such method of finding this vector is to use the cross product, or vector product. So we finally arrive at the cross product. The cross product is defined as n equals B cross C, which is B1, B2, B3 cross C1, C2, C3, where this is obviously the vector B and this is obviously the vector C. And then that's equal to this number here. Now you're probably thinking that's going to be really annoying to remember. It's actually pretty easy to remember. All you got to do is look at the B1, C1 row. So think of it as 3 rows here, and delete the first row, and then just take the determinant of the resulting matrix. And that means that the first element is going to be B2, C3 minus C2, B3, which is exactly what we have here. For the second row, once again, we delete this row, and then we calculate the determinant of the remaining matrix, B1, C3 minus C1, B3, and then we times it by -1. So it's actually C1, B3 minus B1, C3. So C1, B3 minus B1, C3. And lastly, for the last coordinate, we delete the last row, and then just make this into a matrix, and B1, C2 minus C1, B2. So it's pretty easy to remember. Just calculate 3 determinants, kind of like cofactors really, where you delete the ith row, and then calculate the determinant of the remaining 2 by 2 matrix, and then don't forget to times the middle one by -1. Okay, so that's the cross product. Observe that it is also a vector. So n is in bold here, and B and C are bold because they're vectors, and also the actual resulting vector that we get is clearly a vector. It has 3 components. So yeah, you take the cross product of B and C, you get a vector that is orthogonal to both B and C. And this is it over here. Alright, we have an exercise here. Show that n really is orthogonal to the vectors B and C. No problem. If we take B1, B2, B3, and we dot it with this thing, B2, C3 minus B3, C2, B3, C1 minus B1, C3, B1, C2 minus B2, C1. If you write it all out, you're going to get B1, B2, C3 minus B1, B3, C2 plus B2, B3, C1 minus B2, B1, C3 plus B3, B1, C2 minus B3, B2, C1. And then we can observe that we get some cancellation. So B1, B2, C3 cancels with B1, B2, C3. B1, B3, C2 cancels with, where is it? There we go. And the other two cancel. And so we get 0. And similarly, N is orthogonal to C as well. You can do almost the same calculation. And so that means also, just to really mention it in case you didn't hear it the first 2 times, it means that N is also orthogonal to any vector that is inside the plane or parallel to the plane that is spanned by B and C, because any such vector is a linear combination of C and B. It's equal to lambda times C plus mu times B for some real numbers, lambda and mu, and therefore N dot W is also equal to 0 because it's equal to lambda times N dot C plus mu times N dot B, and both of those are 0. So we get 0. Alright, the second part was to show that C cross B is equal to negative B cross C, which is equal to negative N. Not a problem. So C cross B, C1, C2, C3, cross B1, B2, B3, and that is going to be equal to C2, B3 minus B2, C3, and then deleting the middle row, C1, B3, well, actually we have to take the negative of this one, so it's going to be B1, C3 minus C1, B3, and then delete the last row, C1, B2 minus B1, C2, and clearly, so this is N over here, and this is C crossed with B, and so clearly this is equal to negative N. So unlike the dot product where we have B dot C is equal to C dot B, the cross product, if you swap it around, it actually times the result by negative 1. So yeah, that's the cross product. Take 2 vectors B and C, you get a vector that is normal or orthogonal to both of them by using this formula here.